but
So I just want to make, before I will announce the first speaker of this afternoon, was two things. First, there's a poster outside, which you're all invited to put your name on, sign your name, which is for Alex. And the second thing is, I just want to make a little, something about Alex, because I'm not one of the speakers, so this is my only one and only chance. So of course, I knew about Alex for a long time, but it's a funny incident because I had a paper. Well, I gave a talk. I think it was 2008. Sorry?
I'm not sure whether Alex can hear you.
stand under the loudspeaker. Stand
Oh, I
like
see.
here.
Well, I can hear, but the quality of sound is very poor. Perhaps
Okay,
you
maybe I
can
should
speak
stand here.
more directly to the microphone.
So can you hear me now?
Now it's better, yes.
Okay, so it was funny. I gave a talk. I think it was 2008, and it was about a result. I was quite excited. It was a paper by a book in Milner. There was a question, or rather, it was a statement about some classical result of part 2, and I realized I could prove the opposite, or I tried to prove the opposite. So I had a statement. You have a rational map. And suppose all the periodic points have multipliers. So the eigenvalues, the derivative of the map at the periodic points are real. Then I could prove that there's 4 cases. And the last case was sort of a silly case. It meant something like that the Julia set would be the image of some real line, something like that. And Alex was in the audience and said, I can prove that the last case is sort of much simpler. And, the paper really improved a lot because of that. I mean, I was very happy with what I proved, but I was really, really, really happy. And I think Alex even did some work later on related to this. So thank you very much, Alex. It was a nice collaboration. Thank you.
Thank you. Thank you for collaboration as well.
Oh yeah, the talk. That was my attempt to make a joke. So James Waterman, and he's going to give a counterexample to one of the conjectures of Eremenko.
Thank you very much. And thanks to the organizers as well for the opportunity to speak. So I'm going to give a counterexample to Eremenko's conjecture, and importantly, this is joint work with David Martepeta and Waterman. Okay, so to get started, just a little bit of background for those who aren't immediately familiar with complex dynamics. So what we're going to be interested in is maps from the complex plane to the complex plane that are analytic. I'll start off very, very briefly talking about polynomials, and then the rest will just be about transcendental entire functions. So we're going to denote by f to the n the nth iterate of f. So what we mean by this is we're just iterating the function f again and again and again, n times. And what we're interested in is what happens as n tends to infinity. So nicely, our complex plane splits into 2 dynamically interesting sets. We have the 2 set, which is where we have stable behavior, and we have the Julia set, which is its complement, where we have chaotic behavior. So these are our 2 dynamically interesting sets that we're going to be interested in, and in a sense, in order to study them, there's another interesting set, which was introduced in Walter Bergweiler's talk earlier, which is the escaping set. So right now, I just like to do a little bit of a compare and contrast between iterating a polynomial versus iterating a transcendental entire function. But throughout all of this, the escaping set, we're going to define it as the set of points in the complex plane for which, when we iterate, this converges to infinity, is our idea. So for a polynomial, this set is very, very nice. So it's just the attracting basin of infinity. So it's just a neighborhood of infinity. And we can see and relate the escaping set and the Julia set by the fact that the boundary of this neighborhood of infinity is going to be Julia set. And moreover, we have the stable behavior happening on the 2 set. Okay, so again, most of this talk will be about transcendental entire functions, but a little bit of a compare and contrast. So for instance, for a polynomial, the Julia set is always going to be bounded, whereas for a transcendental entire function, the Julia set is always unbounded. Also, one has this famous law of Sullivan that for polynomials, we have no Warning domains, and for transcendental entire functions, Warning domains are possible. One has these dimensions results, and this one due to Baker. And then finally, and a little bit more of an interest for this talk, is that for polynomials, one has a relationship between this basis of infinity, this escaping set, and the Julia set by, one can describe the dynamics of the Julia set by the escaping set. So in particular, one being hand wavy gets external rays, puzzles, and things like this from having nice knowledge of what the escaping set looks like. And there's the question of whether or not one gets a nice description of the dynamics of the Julia set by the escaping set is going to be somewhat what this talk is about, and in particular, what is the structure of this set. Okay, so the escaping set in the transcendental setting is defined exactly the same. It's a set of points for which we iterate, and it tends to infinity. So unlike polynomials, the escaping set is no longer going to be a neighborhood of infinity. The escaping set can meet both the two set and the Julia set, whereas before we just had that it was a subset of the two set, and also, which is also mentioned earlier in Walter's talk, the escaping set can have very different rates of escape. So we're interested in the structure of the set, the escaping set, and it was noticed even all the way back in Fatou's seminal memoir in 1926 that the escaping set often contains actual curves that tend to infinity. And
what's the rate of escape in this context?
So I guess what you can think is earlier Walter talked about slow escaping points of fast escape and things like this. So
What is it?
okay, so if you have a given sequence that say tends to infinity, then you can find points in the escaping set that for which the modulus of this point is always less than or equal to this given sequence after some amount of time. Okay. So that if you had some sequence that tends to infinity very, very slowly, then you could have a point in here that also tends this arbitrarily slowly to infinity. This won't really be necessary for the talk. So, okay, so Fatou, what he looked at, and also Devaney, their approaches were, in a sense, example-based. So Fatou looked at some multiple of the sine function, and what he saw is that there are actual curves inside the escaping set. So here, this gray region are going to be points which are bounded eventually, and this red region here, which computer picture is slightly a lie, consists of, say, curves inside this red region. And what Fatou saw was that there were honest curves here for some particular things. And what he asked was, well, does this also occur for more general types of functions? So Devaney and co-authors, including Tangerman, looked at and tried to study other examples, in particular suitable multiples of the exponential function. And so here is a nice picture where the Fatou set is going to be in white, the Julia set is in black, and what we get is that for this example of interest to us is that the escaping set are just going to be an infinite union of curves without some of the endpoints here. So that's what the structure of the escaping set is going to look like.
How do I understand this picture? Both the Julia set and the escaping set are in black.
Exactly. So
Are they the same?
they are not the same, but pictorially they are the same. So the Julia set is the black with the endpoints, and the escaping set is you remove some of the endpoints. So in a sense, what you should think is that all the dynamically interesting behavior is happening on the endpoints, that on the actual curves themselves without the endpoints, the function's escaping like the iterated maximum. So it's escaping very quickly on the curve without the endpoints, and on some of the endpoints, you have everything else happening.
The right boundary of this picture? Is it what equal to something? What's the right boundary?
It's real part equal to probably something like 10 or 20. So, and it's periodic.
What is 0?
So 10 or 20. So where is 0? 0 should be somewhere around here-ish, I believe. Okay, so here's an attracting basin of some attracting fixed point in here, and you have this picture repeated as you go, because this is periodic.
Okay, so this should be.
So it should be that you look at this picture and it'll be repeated up and down, and you'll have, and yes, it's super. And yeah, you'll have this guy going off, and you have this canter bouquet of curves where if you took some cross section here, what you should at least heuristically see is a canter set. Okay, so motivated by these two specific examples, and Alex can correct me on some history and motivation, and as well as results by Baker for general transcendental entire functions, Eremenko showed following properties in his paper in 1989, which is, first off, that the escaping set always meets the Julia set, that just like polynomials, the boundary of the escaping set is the Julia set, and the closure of the escaping set has no bounded components. So this led to a conjecture of Eremenko, which again, we saw the actual screenshot earlier, which is that it is plausible that the set I of F has no bounded connected components. So this exactly became known as Eremenko's conjecture, and a little while later, it was more formalized into perhaps these two statements. The first is known as the strong Eremenko conjecture, and what you should think is it's saying that every point in the escaping set can be path connected to infinity. So you can find an actual path contained inside of the escaping set from the point to infinity. Whereas Eremenko's conjecture itself says that all components of the escaping set are unbounded. So the escaping set has no bounded components, is the conjecture. So both of these conjectures and Eremenko's conjecture in general has motivated a large amount of progress in transcendental dynamics. And I just wanted to give one more example of what types of structure of escaping set you could possibly have. So one saw for this exponential family, one has that you have an infinite collection of curves here that are all going to be components of the escaping set. And for this one just has one component of the escaping set. It's connected and has the structure of what's known as a spider's web. So what you should think is that you have a whole bunch of loops here and curves here that are going to form what the escaping set looks like. So it's a bit of a messy looking picture. These black regions are going to be bounded basins of attraction, but hopefully it gives you a little bit of an idea of some of the possibilities for transcendental entire functions that are reasonably easy to get hold of. Yeah.
Is it dense?
No, I don't think it should be dense. But this is, I have to think. Okay, so for a general transcendental entire function, what's actually known about the escaping set? So in general, I think general idea should be the takeaway that if you want to try and control the components of the escaping set and what they actually look like, this is incredibly difficult. So Ripon and Stollard showed that if you take the escaping set and add in the point infinity, then it is in fact always connected. So you should think like, for example, this exponential function that we had before. If you take the point infinity and add it in, even though before one had infinitely many connected components, now it's all connected. And this is true for every transcendental entire function. And if we had a bounded component of the escaping set, then it would have to meet the Julia set. Also, by results of Ripon and Stollard, the escaping set always has to have at least one unbounded component, and either the escaping set is connected, just like the spider's web example that I showed before, or it has infinitely many unbounded components. So
IFF meets GFS means non-empty intersection, or closure is non-empty?
non-empty intersection. Yes. Okay, so just a quick reminder about the strong Eremenko conjecture, which says that we can have a point, that points in the escaping set can always be path connected to infinity. Well, it's known that this can fail. So Rempe, Rodenfuser, Ruckert, and Schleicher construct a transcendental entire function so that every path connected component of the Julia set is in fact bounded. And for these functions, one has that the escaping set is a subset of the Julia set. So this gives a counterexample to the strong Eremenko conjecture. And also, they at the same time show, as well as subsumed in here, our results of Baranski, that the strong conjecture does hold for some large class, which in particular includes class B of finite order. So there are some cases where it's been confirmed, and there are some cases where the strong Eremenko conjecture has counterexamples have been found. And there's many other counterexamples that more or less are whether or not one changes particular restrictions on the function or on the types of structure that one actually gets, is the idea. Okay, so together with David and Lassa, we give more further wide range of counterexamples. So pick your favorite, whatever it is, compact connected set with connected complement. So if you want, it could be a basilica or some other compact connected set. Then we can realize this exactly. So in the dynamical plane of a transcendental entire function, for which every path connected component of this set is also a path connected component of the escaping set. What you should imagine is, for instance, you have a basilica here, and you have something that isn't in the escaping set that's sort of separating it out, is a heuristic picture that you should have in your head. And moreover, one can ensure that every path connected component of the boundary of this set that you can choose to prescribe is a path connected component of the Julia set. So in particular, this gives a further wide class of counterexamples to the strong Eremenko conjecture. Okay, so back to this result, to this conjecture of Eremenko. So again, this conjecture of Eremenko says that all components of the escaping set are unbounded, is the conjecture. And together with Lawson and David, we construct a transcendental entire function so that the escaping set has a single point that is a connected component of it. So this gives a counterexample to an conjecture. One has this bounded component, which is a single point. So not only that, but again, whatever your favorite non-empty connected compact set is, it could be, for instance, the Julia set of some quadratic polynomial or something like this, as long as it's connected compact and it has connected complement. So whatever you want, then we can realize it exactly in the dynamical plane of a transcendental entire function, for which this is actually a connected component of the escaping set. So we give a very wide range of counterexamples to this conjecture of Eremenko.
But they're all infinite order.
So yes, our construction, so I will get to this. I'll get back to you. Okay, so I'd like to talk a little bit about the construction. So I suppose one could think of the construction having two parts. So the first part is one needs to know what the structure of the function or the counterexample that we want would be. So what does this function actually look like? How does it act? So that's the first part. And the second part is, well, once one has this idea of how this function actually acts, how do we realize this as an actual transcendental entire function? Are the two pieces. And very broadly, heuristically, what we do is we give a new general framework for constructing transcendental entire functions, which have particular prescribed interesting sets of points with nice dynamics that have unbound orbits. Okay, so this realization part is perhaps the easiest thing to start off first. So very broadly, the construction result that we use is an inductive construction that makes use of a classical result from approximation theory. So the classical result from approximation theory that we use is Arkelian's theorem. So Arkelian's theorem tells us that if we have a closed subset of the complex plane and it has these two nicety conditions, the first is that if you look at the complement, it's connected, and the second is you have this nicety condition at infinity, then if you consider some model function, you can approximate it arbitrarily closely by a transcendental entire function. Is very vaguely the idea. And what we do is we inductively apply this result. So to answer the question over here is that this gives us very good control on the sets A, where we want exactly what the dynamical behavior is, but off of it, it gives us almost no control. So yes, the construction that we have, in fact, it's going to be clearly not a finite order, and also clearly not a flat B for the exact construction we have. Okay, so just to say a little bit on what the construction should look like and what exactly are the main things that we want. So first off, what we want to get is a point connected component of the escaping set. So to do this, what we're going to do is try to get a ray that's a connected component of the Julia set, as prescribed exactly. And then from there, so we want that this ray is a connected component of the Julia set exactly. And then from there, we want that this point is in the escaping set, but all the other points on this ray are not in the escaping set. And so then what we'll have done is nicely separate out this point here in the escaping set from any other point. And so in order to do this, in order to get the Julia set here is an actual ray, what we want to do and what we prescribe is somehow that one has that in each of these U-shaped domains, one has a two component that limits. So this one has a two component, this one, that accumulates on the boundary of the set, so that one actually realizes this ray here as a subset, as not just a subset of the Julia set, but actually a connected component.
So those little dots represent the images of the.
So these little dots represent the fact that one wants to continue further and further down. So you should think that this box here is accumulating on this ray.
It's maybe worth saying that the two components are not in the escaping set.
So this is, yes. So the two components are not in the escaping set. Although one also, so if these two components were in the escaping set, you would also still conclude that this ray was in the Julia set. Should be.
Yeah, it's in the Julia set, but
Yes, but you couldn't conclude, you're right, you couldn't conclude that that point was a connected point of the escaping set. Okay, so there's this picture, and now in the last few minutes, a more complicated one is, so what we wanted to do was prescribe, again, this point's in the escaping set, everything else is not in the escaping set. So this point should somehow run to infinity, whereas everything else should somehow clump together and remain, that it doesn't just nicely march off to infinity. In order to do this, what we want to do is, let's say we start off with, here we have what we had in the previous slide. So take this picture and just move it to here. And we want this white dot here to be in the escaping set, and we want this ray to not be in the escaping set. So what we prescribe is that this box, it just wanders up for a bit, say by translation, until it reaches some point, and then we want to map it back down towards some base level in such a way that this point here that we want to prescribe in the escaping set gets mapped pretty far off to the left here. And at the same time, that if you take 2 points on this ray, that they contracted together is how we want to map. And then we continue this process that we map back up in such a way that this point to the left stays far off to the left, and we continue this, and then this point here is going to wander nicely off to the left this way, whereas any 2 points that are on this ray are going to stay, that they'll go up and then back down, but you're going to have some subsequence for which they eventually stay inside of this region here. Okay, so I think that that's more or less what I want to say about the brief sketch. So there's only one more thing, which is thank you very much for listening, and happy birthday, Alex.
Any questions?
Yeah, can you go back to the previous slide and say what that little circle is telling us?
Which one? This one?
Yeah.
Okay, so this is that, remember I said that here I want a F2 component that's in here. In order to get this, what we do is we map this whole, basically you can think region, into an attracting base. So you want to do this at each stage
Separate the F2.
to separate the F2. Yes, exactly.
You have like Z squared on.
I have a, can I?
Yeah, of course.
I have a little historical comment or maybe question, I don't know. I don't think I ever made the strong conjecture.
No, you did.
At least it is not in my paper. I just checked.
It is in your paper. You say it is plausible that every point can be connected to, and we cite it in the RRS paper with a reference, so you can find it there.
I said that it is plausible that every component is connected.
It is the last sentence of your paper. It says it is
The
plausible that the set
I
I of f
see.
always has the following property. Every point z in I of f can be joined with infinity by a curve in I of f. Thank you.
Okay. Okay. I just didn't read to the last.
You have other questions, Alex? No. Any other questions? Okay, well, let's thank. Thanks again.
Exactly. When you do these things, you like, so you first define the lower guy,
Yes.
and then
You like march up, and then you
march up.
say
Every time you march up, you do a
do it-
pasting to the Herculean.
exactly. Yes. And so I can preempt, I think, your question, because do you think you would just
No,
no? Okay.
no, that is not my question. That, you would have a problem with Herculean in that.
Yeah.
I know that, but you probably know Letty has been harassing me about doing this.
Yes.
And I keep telling her that I don't think it's possible. For reasons. Reason A is the fact that you use like full strips,
Yes.
and then there's a theorem that tells you that you can.
Right.
But more than that, I think I've been bothered with the fact that you might want to have more and more accurate bound on the thingy below. but
So-
that might just work.
I kind of already had an idea.
One thought is something that Letty said, you can do this thing for sure,
Yeah.
and then it could be.
All right, so the next speaker this afternoon is Mokana, who is going to talk about when the circular dilation at a point equals 1. The floor is yours.
Hello, happy birthday, Alex. I have a special connection to Alex. I knew him before I met him because of his advisor. I had the honor of visiting Anatoly Goldberg while I was a PhD student in Lvov. At that time, Lvov was a closed city, and foreigners, even from the Eastern Bloc, where I was from, couldn't go there. But somehow luck was on my side, and I was in Lvov for about a week. And that changed my life. At that time, Goldberg used to talk about Alex with great admiration, predicting all of what Alex will be by now. So happy birthday, Alex. Become what your advisor was seeing in you. And so my talk is, let's see, I also got an invitation very recently, so maybe my talk has more slides than necessary. You know how you have to cut things. And thank you for inviting me. It's great to be here. So what I'm going to talk about is something I've been thinking about over 30 years or more. It's a very basic, fundamental, and classical issue of complex analysis. I'm going to mention a couple of people in this room who have used such results, so stay tuned. And it's about QC maps, which maybe not all of you have used or know about. I will try to be as intuitive as possible. I have 34 pages, so I may or may not go through all of them. So I'm going to talk about geometric and analytic conditions implying certain local behavior of QC maps at a point in the plane, which means I'm working with one-dimensional complex maps, where the circular dilatation or linear distortion equals 1. Special cases of those kinds of maps are conformal maps at a point, C1 plus alpha conformality, asymptotic homogeneity, weak conformality, maximal stretch. These results involve extensions of Teichmuller-Wittig-Belinsky's theorem, and besides being of interest by themselves, they have applications in Neven-Lina theory, in modulus of continuity studies, complex dynamics, the theory of p-integrable Teichmuller spaces. So I'm gonna provide 3 examples of applications that have opened my eyes to those I've been studying them. So here is what I'm gonna talk about. And we will dive into infinitesimal. So I'm just going to focus on a very specific behavior around the point. Just to make sure everybody follows, it's we're working with the domain in the complex plane, homeomorphism in the complex plane, and I'm sorry, in the domain, and Z0 in the domain, and then we define the unit disk, whatever, D of Z0, R, center Z0 radius R, and then we start looking at the circular distortion. So take a circle of radius R0, centered at Z0, and circular distortion will be measuring how much that circle deviates the image, it deviates from a circle. So you have a circle, you map it onto a closed curve by a homeomorphism, and you look at how far is that curve from the image of the center.
So assume F is a homeomorphism onto its image, not a homeomorphism to C, right?
Of course, yeah. It's in C, yeah. So, yeah, it's from omega into a F of omega. And so the circular distortion will be the ratio of the maximum over the minimum distance. And the circular distortion is that, but the circular dilatation will be the lim sup of that ratio. So what happens is we shrink the circle to a point and the curves shrink to a point, and we still look at the ratio of the max over the min, and that's called the circular dilatation. So there is a metric definition of quasi-conformal maps, which says that if the circular dilatation is bounded everywhere by a constant, say m, less than infinity, and if the circular dilatation is less than or equal almost everywhere than k, then we have a k quasi-conformal map. That's a metric definition. And the k quasi-conformal maps enjoy a lot of analytic properties. We define the z and z bar derivatives of those, and we can talk about absolute continuity on lines, which implies almost everywhere differentiability. We can find delta f in terms of fz and fz bar derivative, which exist almost everywhere, and then this is differentiable function almost everywhere. So when we go to the tangent plane, when we go to infinitesimals, basically we work with linear functions, and infinitesimal circles go into infinitesimal ellipses, and the maximum and the minimum distortion on that circle are computed in terms of the complex derivatives. So I drew a picture of the image ellipse, and you can see the minimum and the maximum axis, the maximal and the minimal axis. And besides that, I have drawn the directional dilatation derivative of the map F alpha, which is defined in this particular way. So what I would like to say is that usually one works with the so-called real dilatation. The real dilatation being the ratio of the maximum over the minimum axis of the ellipse. But in my studies, I moved to the directional dilatation, which deals with the directional derivative. So the goal here is to provide analytic and conformal modulus estimates that assure that behavior around a point has a circular dilatation equal to 1. Did I define what it means to have circular dilatation equal to 1? The circular dilatation equals 1 means that the circular dilatation is equal to 1. So somehow the image of a circle, when it shrinks to a point, is becoming more and more like circle. Now, some people are quick to conclude this is conformal. So that's where I'm going for the whole hour. It's not. So the real dilatation, as I said, is the ratio of the max over the min of this axis, of this ellipse. And the directional dilatation determines the ratio here of f alpha squared over jf, and that always is bounded by one of the real dilatation and the real dilatation. So when one talks about conformality at a point, if one is interested in it, one usually measures the deviation of the real dilatation at the point from one, or rather the deviation of the real dilatation in the whole neighborhood. And when you look at the directional dilatation and subtract one from it, two quantities immediately pop up. One of them involves mu f squared, and the other involves the real part. So when we try to improve on results involving integral condition on d minus 1, we are going to work with df directional dilatation minus 1. Interesting thing is, if you look at the work of Teichmüller, which I had the honor and pleasure of translating, it's a Habilitationsarbeit for the 7th volume of the handbook on Teichmüller theory. He really nicely explains from the picture you see here why the Jacobian is given by this formula. So looking at this picture, since we work with the infinitesimals, the Jacobian will be the ratio of the areas of the ellipse over the circle. The area of the ellipse is the product of the axis divided by the area of the circle. You get the Jacobian. So this guy is the product of the axis. So the measurable Riemann mapping theorem states the existence of solutions of Beltrami equations with coefficient that is with L infinity norm less than 1. And I'm going to sometimes state my results in terms of mu homeomorphisms, which are a slight generalization of quasi-conformal maps for which the complex dilatation is not bound. So here are some examples that provide various cases of circular dilatation equals 1. So the first example is the figure 1. Certainly, if f of z over z has the limit as z goes to 0, then the circular dilatation at 0 is equal to 1. So we work with 0 going into 0, and omega contains 0, and f of omega contains 0. The second example is very well known. It's called, I don't know what it's called, but it's Shabbat's example. You look at z times 1 minus log absolute value of z. Well, this actually preserves radii and maps circles onto circles. So clearly at 0, the dilatation is equal to 1 because circle goes into circle. In addition to that, the complex dilatation, which is calculated here, can be seen as approaching 0. Such kinds of maps for which the complex dilatation goes to 0 are called asymptotically conformal. However, they are not conformal. Certainly, f of z over z doesn't go to a constant. It doesn't. So another example is where we multiply the identity map by some sort of a spiraling coefficient. And this map here has complex dilatation that actually goes to 0 and circular dilatation equal to 1. In this case, circles are mapped onto circles, but radial stretches are mapped onto spirals. The same is true for this map. Circles mapped onto circles and radial segments are mapped onto spirals. However, the complex dilatation doesn't go to 0. So somehow, the complex dilatation doesn't go to 0 when you spiral a lot. And you don't have asymptotic conformality. And the last case is the most unusual one, where we look at the stretch map that is usually used to prove that the condition on Lipschitz continuity of the quasi-conformal map is 1 over k. Surprisingly enough, it has circular dilatation 1 because it maps circles onto circles, and at 0, the circular dilatation is equal to 1. Not only that, it actually is differentiable everywhere, and the real dilatation is actually equal to k. So no, the complex dilatation is k minus 1 over k plus 1 times e to the times c to the double the argument, but the real dilatation actually is equal to k. So for such map for which the circular dilatation is 1, the real dilatation goes to a constant as we approach the point. So these are the 4 examples that highlight how diverse and complex the behavior is depending on what the map is. If you have a lot of rotation, your dilatation may not go to, the complex dilatation doesn't go to 0, the real dilatation doesn't go to 1. So this will be addressed. In addition to that, here is an example of Goldberg that he shared with me at the time I visited him. Then you can construct a map which has a circular dilatation 1, but it's not conformal, and its real dilatation approaches 2. I'm sorry, it's conformal, but the real dilatation approaches 2. So in order to understand this, I will refer to a work of Teichmüller from this Untersuchungen über Konforme und Quasi-konforme Abbildung. That's his habilitation work. He actually gave sufficient and necessary conditions of a homeomorphism, not necessarily quasi-conformal, to have a circular dilatation equal to 1. The proof is based on a theorem called Teichmüller's model Satz, and I have listed it here, but for the sake of time, I'm gonna just explain what the Teichmüller's model Satz does in words. If you have, we are working with conformal modules. This is something that Teichmüller developed in his work very well and explained very well. In general, the conformal module of a ring domain is 1 over 2 pi, the logarithm of the ratio of the radii of the boundaries of the angle. So if you put a curve inside that, you might want to figure out under what conditions on the module the curve actually is getting closer and closer to a circle. Well, that's the circular dilatation kind of question. So when is this curve very close to a circle is based on the following observation. The module of the green ring annulus is always greater or equal than the sum of the 2 smaller ring domains. So you have, it's natural to this condition is very natural to see that if the sum is very close to the whole, so the sum of this ring domains, the modules of the sum, the sum of the modules is very close to the module of the ring domain, then maybe the curve is very close to a circle. And so there are very, very fine estimates in this direction. And one can prove that if the 2 modules m prime and m double prime add up to 1 over 2 pi logarithm r over r, then this curve is a circle. So what Teichmüller was after is studying the type questions, the type problem of a Riemann surface, hyperbolic, parabolic. So he needed to develop to do that, and somehow went into the direction of the Teichmüller-Debye theorem. So he provided sufficient and necessary condition for a quasi-conformal map defined in a neighborhood of infinity, which I changed to 0, to be having a circular dilatation equal to 1. And he expressed that condition in terms of a sequence of modules of annuli as they shrink to the point. So instead of having like So we take circles here, they're mapped by a quasi-conformal map onto ring domains, and then we're looking at the modules of the images, and we want the module of the subdomains to get closer and closer to the module of the union. So using that result, he's able to prove his theorem. So I'm not going to go through the details. His theorem says that if W is a quasi-conformal map, say from the disk into the disk, f of 0 equals to 0. And then if majorizing function C of R minus 1, the R over 0, 1 is that integral is convergent, basically referring to the difference between the dilatation and 1 is getting smaller and smaller. Therefore, we have that the absolute value of f of z is behaving like a multiple of absolute value of z. So that's his theorem, and Teichmüller-Wittig's theorem slightly is changed here, where the majorizing function of d of z is replaced by the real dilatation. So
If you use the pointer to show it to, then Alex can also see where one point. You know what it is?
I can use that.
Ah, sorry, it's your own tablet. Ah, yeah, or like that, yeah.
So I'm do this when I teach. So what we are looking at is conditioned by Teichmüller and conditioned by Wittig, but Teichmüller knew that Wittig's condition worked. It was just a rough estimate. He didn't just do it. So the Teichmüller-Wittig theorem says that if W maps quasi-conformally the disk into itself and 0 goes to 0, and the real dilatation is in some sort of integral condition on the real dilatation minus 1, is that integral is convergent, then we have a stretch, which is kind of part of conformality of 0. An interesting remark I heard for somebody in the audience is that he studied how quickly that integral is converging to 0 when we have the integral from 0 to r, right? This is, of course, the r over r, but sorry, I made a mistake. So here it is. You looked at the integral from 0 to r, C of rho minus 1 d rho over rho. So you looked at that and discussed for a while, what if it converges to 0 at a power of r? And he concluded that the best possible estimate for the difference here is an expression that looks like that. So I'm going to get back to it in a bit. So that's kind of something that I wanted to mention for the moment. So Teichmüller-Wittig-Belinsky theorem extends the condition of Teichmüller-Wittig, saying that if the integral converges over the unit disk of the quasi-conformal map, then we have conformality at a point which at 0 is translated to the existence of the limit of f of z over z equals gamma. And so there is a 1 million improvements of that result. So I'm kind of going to describe them rather than go through them in detail. Looking at the integral of the directional dilatations is very helpful and weakens the conditions. So Reich and Walczak in their studies, Edgar Reich from quadratic differentials, improved on Teichmüller-Wittig theorem by pointing out that one can actually work with directional dilatations, and if only assuming a certain convergence of integrals for 2 directions of the directional dilatations, one doesn't get conformality, one gets stretch, which is described here. And one can estimate that there is some sort of rotation of the argument of the map that is not too fast. However, if one assumes that the integral is convergent for 3 directions, then one gets conformality. Rankin-Walchuk had a very nice conjecture saying that every measurable function that is a potential real dilatation in a domain can be matched with a quasi-conformal map, which has the same real dilatation and it's conformal at the point. That conjecture is actually unsolved. No matter what your real dilatation is, you can find another map, quasi-conformal in, say, in the disk, which is conformal at that point and has the same real dilatation, emphasizing that the directional dilatations catch something about the map that the real dilatation doesn't. So the real dilatation is not enough to conclude conformality always. Like you can always pick an example where you have conformality with any real dilatation in a domain. Later on, I've worked with James Jenkins on this question and ended up with a little bit stronger condition for conformality, showing certain asymptotic rotation if certain conditions are not completely satisfied. And later on, Gutliansky and Martiu broke down further the conditions for conformality, and that was a very strong paper. So that was considered the state of the art for a while. And Gutliansky and Martiu in their paper actually solved the Reich conjecture for a very special case. For the case where you know that the absolute value of the complex dilatation squared is integrable in with respect to the logarithmic metric. So, you know, when you talk about absolute value of complex dilatation, that is an expression of the real dilatation. So, since I like conformal modules, I proposed later on in 2010 a bunch of conditions that involve modules of ring domains or families of curves that are sufficient and necessary for conformality. Now, conformality with analytic conditions, sufficient and necessary conditions, is not possible with analytic conditions, but with modules, you can always come up with a sufficient and necessary condition, which is kind of a final say in the subject. I am not gonna bother you with that. If just this is a very long theorem, but it gives sufficient necessary conditions for conformality using conformal modules, ring domains as well as curves that are spirals. And using that theorem, I was able to reprove what Gutliansky and Martiu had in a very different language, which involves directional dilatations, similar to what Reich and Walchuk had in their work, except that it doesn't have absolute values inside here. So Reich Walchuk had absolute values. I don't. So these are like very specific improvements on the conformality at the point. So one might want to know when one has C1 plus alpha conformality, something defined in a paper of Shishikura recently published in 2018. If anybody would have told me that I'll give a talk about the work of Shishikura when Shishikura is right here and he's going to give a talk after me, I wouldn't have believed it. So
only in America, it's possible.
In America,
Only in America is everything possible.
But
I understand, but we say it anyway.
all right. It feels like America. So we have here is a beautiful result using quadratic differentials that is C1 plus alpha conformality of importance to dynamical systems. That's how far I can go. I know that McMullen proved that result and used it in his book. One of the two books, I don't know which one, but this result is really proved with different methods. And it says that in addition to having conformality, you have some sort of an upper bound. One assumes that the rate at which this integral goes to 0 is of order r to a constant. So it's kind of a power of r. And then one proves that for any alpha between those two numbers, 0 and beta over 2 plus beta, f of z can be expressed, f of 0 is 0, f prime of 0 times z plus O capital of absolute value of z1 plus alpha. So there is this c1 plus alpha formality. Looking at that expression and looking at Teichmüller's work, it's very natural to ask that conjecture. I think I have almost gotten it, but I'm not sure in the details because Teichmüller works with the logarithmic plane. And when exponentiating his results, I get an extra constant that becomes power and it ruins everything. But looking at Shishikura's result and my result, it's just a slight extension of what Shishikura has. And basically, this result is sharp because it uses the Teichmüller's model sets. So anyway, I'm happy to discuss this if anybody is interested, but this is like almost done deal if one knows how to undo the logarithmic plane. If it wasn't the logarithmic plane, it would be true. So there it is. And there is a beautiful result by Scheffel and Nikolaev, who are looking at Peano derivatives at the point, and that result has a similar flavor to the C1 plus alpha conformality, but here there is an existence of Peano derivative. So there are many tools for studying, to jump to the end of the talk, the universal Teichmüller space and smoothness of it, which is something I'm very interested in. Smoothness of the QC maps, quasi-symmetric maps on the real line. Anyway, so here I want to get to approximate continuity because that explains a lot. The approximate continuity is a concept that says, well, the function goes to a limit over a set for which the point toward which z goes to is a point of density. So you don't have completely going to a limit, but almost going to a limit. And so the idea is approximate limit of mu of z is mu naught, real analysis stuff. If the limit is mu naught over a set for which z naught is of density 1. And remarkably nicely, this is discovered by Razanov and Gutyansky in Ukraine. Those points of approximate continuity are actually Lebesgue points because mu is now infinity. And because of that, we can move between the two Lebesgue points at z naught versus approximate continuity and get a bunch of beautiful results. So here is a definition of what's coming up, that is generalization of conformality. If a quasi-conformal map is from a domain omega into C, such that 0 goes into 0 is asymptotically homogeneous, we define asymptotic homogeneity by, zeta comes in front as the limit. F of zeta z over f of z is not equal to zeta, but goes to zeta as z goes to 0. So you have asymptotic homogeneity, which is equivalent to a conformality in terms of Belinsky. Circular dilatation equals 1 at a point. Reservation of annuli, rotations along a circle. And the most interesting part here for me is that the growth of the dilatation of the function, logarithm of the growth of the function, sorry, Alex, here, that is a very interesting property to me. When u is a Lebesgue point, the solution to the Beltrami equation behaves so that logarithm of absolute value f of z over log of z approaches 1. A lot of geometric things are happening, but this one is pretty amazing. So what is this telling you is that the absolute value of f of z is approaching 0 at a certain rate that's not too fast. And Gutliansky-Ryzanov's theorem says that if the approximate limit of mu f, so if we have a quasi-conformal map from the complex plane onto the complex plane, f of 0 equals to 0, approximate limit of the complex dilatation approaches 0 as it goes to 0, then f is asymptotically homogeneous at 0 and satisfies all of these properties. So this is 5 here. Sometimes the property 2 and 4 are called weak conformality. They're not conformality, but they're weak conformality. And so here comes this equivalence between approximate continuity and Lebesgue point as 0 when we work with 0 as the point. And you know that when mu f is asymptotically conformal, then everything falls into place and it's a Lebesgue point and stuff like that. So one might wonder what happens if we have convergence of any power of mu. That convergence here, p greater than 0, instead of just 1, the power of 1. And it's easy to see that that implies that mu is approximately continuous. So it's under that condition, the convergence of this integral, where p is not necessarily 1, but any number between 0 and infinity, not 0, then we have mu must have a Lebesgue point to 0, and the map is asymptotically quick, homogeneous, which means it has circular dilatation equal to 1. So when I was in Lvov, I proved the theorem involving mu f of z squared instead of 1. You see this is a weaker condition than 1 because mu is less than 1. When you square it, it gets smaller. So the integral of mu z squared is over absolute value of z squared is going to be smaller. So it's not going to imply conformality. And I was able to provide an asymptotic behavior of that and show that this is asymptotically homogeneous without knowing Ryzanov and Gutliansky's result. In addition to that, if mu satisfies the conditions of Techno-Levitic-Belinsky theorem, we get the Techno-Levitic-Belinsky theorem. So now about applications. Reason used extension of Techno-Levitic-Belinsky's theorem, which is really pretty cool. I took it from one of his papers, not necessarily from the original paper with Weizmann. It's a paper called On Techno-Levitic-Belinsky's Techno-Levitic's theorem. What he considers is the point at infinity, which is really substitutable with 0, 0, 0, infinity, infinity. So if on rings of aspect ratio 2, over those rings as they go to infinity, this integral is behaving like O small of 1, then he concludes that this supremum is O small of 1, which implies circular dilatation equals 1. It turns out that he gave a very ingenious. I like the proof. I believe in it. You believe in it? But you can find a 5.
Was in America.
This was not. Was. The proof of this theorem is done in a much more complicated way in the proof with the paper with Weizmann, about 5 to 6 pages. Maybe I'm making this up. An immediate consequence of this theorem is circular dilatation is 1 at infinity, which is equivalent to 0. So that expression here really bothered me. I said, this, I've seen before that. I've seen that before. So what is it? It's the Lebesgue point. That condition is equivalent to Lebesgue point. So I was able to prove it like before the conference. So under that condition, we have Lebesgue point, and not only have what David has, but we have also all kinds of conclusions that go with asymptotic homogeneity. So I believe it's true that if Dresden's condition holds at 0, Weizmann, Dresden, Dresden, Weizmann, Dresden, then even only if the mu is approximately continuous and goes to 0. So what do? You use the ubiquitous Hölder inequality. So Hölder inequality saved my life all the time. Anyway, if I have time, I'll go through it, but that's what basically we have asymptotic homogeneity. And in his papers, Dresden says this generalization of Technolytic theorem has played a key role in this paper, and in the solution, I'm not sure, possibly of solving the inverse problem. So I'm going to move to a next application, which is maximal modulus of continuity. As I showed you, there is this map, which is Lipschitz at 0 with a constant 1 over k. It's the extremal map. It shows the Lipschitz continuity cannot be improved. That map is called Fk. And so we can look at that map and say, what happens is here we have circular dilatation equal to 1 because circles are mapped onto circles. However, everywhere we have differentiability where infinitesimal circles go into infinitesimal ellipses with maximum axis k, minimum axis 1. So we have kind of a stretch everywhere. So that's why the real dilatation is always k. And somehow in 1997, James Jenkins and I gave a proof of a theorem that implies asymptotic, I'm sorry, Alex, that implies this condition when sufficient condition for f of z to behave like a stretch map. I mean, what's it called? Maximal stretch map. And that was used in Kovalev's paper to provide local modules of continuity results. So that's another application of circular dilatation equals 1. Results implying maximal stretch results for quasi-regular and quasi-conformal maps. So these are very interesting results in my opinion. Points of maximal stretch map into points under F that are far away from each other, which is this condition. So here are how a point of maximal stretch is where the modulus of continuity. This is the modulus of continuity, and then this is the limit of the modulus of continuity. So it's not always going to be 0. Here is the f omega f of z naught. So this is the limb soup of the modules of continuity over delta to power 1 over k. That's not always 0. So when it's not 0, one talks about points of maximal stretch. And at those points, Kovalev gives a very nice result, which is kind of reminiscent of conformality. That's the third kind of connection to maximal stretch. Now, Kovalev was commenting in his paper, oh, we have really strange conditions here. We have circular dilatation 1. How was that? The circular dilatation is 1, but we still have like everywhere K as dilatation. So it's really kind of counterintuitive. You wouldn't expect K to be the dilatation to be everywhere K and just have circular dilatation 1. But if you look now at the pictures, it makes a lot of sense. So the last application is in the p-integrable Teichmüller spaces. I was going to go over what it means to talk about boundary correspondence and then define the universal Teichmüller space and then the p-integrable Teichmüller spaces afterwards. So a quasi-conformal mapping of a Jordan domain onto a Jordan domain can be extended to the closure as a homeomorphism. Study boundary behavior of QC maps. One often considers quasi-conformal automorphisms of the upper half plane or the unit disk. So if we have a quasi-conformal automorphism of H, F infinity equals infinity, the induced boundary correspondence, which exists, is also denoted by F. And if you extend it by reflection, you have a quasi-conformal map of the complex plane onto the complex plane. So of great interest to many analysts and geometers and topologists is the so-called interval distortion of the boundary map that takes the real line into the real line. And the interval distortion here is defined as this ratio, which basically takes a symmetric interval into some non-symmetric interval, and you look at the ratio of the two sides. And we are having a point x plus t and x minus t, and they are mapped into some other point, f of x plus t, and f of x minus t. And we divide this over that, right? And we call this the interval distortion. So symmetric interval is part of a circle, and that gets into some sort of a curve here under the extended quasi-conformal map. And you can easily see, because of the metric definition, that the ratio, the interval distortion, have to satisfy this property, because the circular dilatation is always bounded. Certainly, that is a property that has been used to define quasi-symmetric maps, and then one knows of a very well used theorem by Alfors, which says that if you have a quasi-symmetric map, you can extend it to the upper half plane by using this formula, and it's continuous and so on. It's a very powerful result, saying that quasi-symmetric maps have quasi-conformal extension. Vice versa, if you have quasi-conformal map from H to H or from D to D, then the boundary extension is quasi-symmetric. So those results have been discussed in a paper by Carlson, who was really interested in under what conditions the boundary correspondence between R and R of the half planes is actually behaving nicely, absolutely continuous or differentiable. So he first gave these powerful results that are based on the behavior of the quasi-conformal mappings dilatation near the boundary. Those results have been extended beautifully by many authors. And we don't stop here, but kind of go to the definition of symmetric maps. Because there is quasi-symmetric, there's symmetric maps, and we can talk about them on the circle, on the real line, and asymptotic conformality, and all these things come together to develop a whole theory of Banach spaces. And we are looking at quasi-symmetric map as a map on the real line, which has the property that the interval distortion is bounded by a constant. We talk about symmetric maps if the interval of distortion is approaching 1 as the length of the t of the interval x minus tx plus t goes to 0. And using the exponential or even the Möbius transformation, we can translate those results to the circle. And we talk about quasi-symmetric and symmetric maps on the circle S. I forgot to define that. Here it says S is the unit circle. So the universal Teichmüller space takes all quasi-symmetric maps on the unit circle, fixing one. So we define the universal Teichmüller space simply, one of infinitely many definitions, as the space of quasi-symmetric homeomorphisms of the unit circle fixing 1, I, and -1. One can talk about equivalent classes, but I like to fix those points. So you have just quasi-symmetric maps on the real line, that's universal type. However, things get much more interesting when one talks about equivalent classes of complex dilatations or equivalence classes of quasi-conformal maps of the unit circle. And one develops all this Beers theory about Beers embedding, and develops the through the Beers embedding Teichmüller and Kobayashi metric and complex Banach manifold structure, which is things that have nothing to do with circular dilatation equals 1 for the moment. But they do, because if one looks at, so there are so many results in this direction that I probably will not go over, but these are the main topics, look at the subspaces of the universal Teichmüller space and study them in logical or complex analytic way, metric way, and talk about structure, complex Banach manifold structure, or talk about Teichmüller metric and Kobayashi metric. So great directions for studying those is in Lehto and Markovic and Fletcher. And finally, I come exactly to the end of the talk, where I can introduce how circular dilatation equals 1 relates to proving that the integrable Teichmüller spaces are symmetric. So the integrable Teichmüller spaces are subspaces of the universal Teichmüller space, and they can be defined as this is T of D. So we work with unit disk at the moment. Let's see. All right, all this is T of whatever. This is the universal Teichmüller space. So look at the quasi-symmetric maps. And you say that the quasi-symmetric map belongs to the P-integrable Teichmüller space if and only if there is an expansion that satisfies an integral condition, a convergence of this power of the complex dilatation with respect to the hyperbolic measure. As you can see, that expression is exactly what we've been using. So no surprise here. I can show that every map that is in any P-integrable quasi-symmetric map that is in any p-integrable Teichmüller space is symmetric. Because the trace of a circle on the line is symmetric interval. So that's how one can prove things. In addition to that, one tries to describe intrinsically the integrable Teichmüller spaces, and Bessel spaces come to play a role. And it turns out that Julian Scheng result, which was only about Weil-Peterson Teichmüller spaces when p equals 2, can be extended to any p greater or equal to 1. He just recently published a paper in which he actually proves for p equals 1 that the Bessel spaces, no, for p greater than 1, I'm sorry. If a map belongs to the Bessel space, quasi-symmetric map, then it's if and only if it's in the corresponding TP space. Well, for p greater than 0, we have symmetric maps. When p gets smaller and smaller, p less than 2, less than the Weil-Peterson space, Weil-Peterson class, things get more and more smooth. And that's where results like C1 plus alpha conformality, Peano derivatives play a role. These are these line spaces. What can we say about the extension is 2D. Earl's extension in those spaces is Alfors-Berling extension in those spaces. There are all kinds of questions. What is the intersection of all those spaces, the union? They're all subspaces of the symmetric spaces. So these are all kinds of interesting questions. And finally, Teichmüller-Wittig-Belinsky plays a role in proving that T1, the one integrable Teichmüller space, is smooth. So if you're in T1, then the quasi-symmetric map is actually continuously differentiable. And that's an application of the theory that I was discussing. And I think I'm 5 minutes ahead of time, which I love when I finish my lecture with my students. I hope I didn't quite brush off all the details and gave you an idea of what I'm working on. And it's not quite complex dynamics, but I have great interest in complex dynamics. I follow the talks and I'm really interested in applications. And I really appreciate having David Drazen and Professor Shishikura here, who are probably using such results in their research or have used them. So, I mean, thank you, Alex. Happy birthday. I wouldn't have been here without you and the organizers who decided to give me a chance. Thank you.